Hello, welcome everyone. In today's lecture, we are going to look at some examples of applying Castigliano's theorems for evaluating the rotations and deflections of different structures. So by the end of this lecture, you will be prepared to apply Castigliano's second theorem for calculating the deflection and rotation of cantilever beams under different loading conditions. In the subsequent lectures, we will look at different types of beams like simply supported beams and so on, or in some cases even more complicated beams. But in today's lecture, we are going to just look at two examples that involve cantilever beams, but they are a little bit different from what you have seen before. Okay? So let's look at the first example. So in this case, you have a cantilever beam that is subjected to this force P at the tip, but instead of being asked to calculate what is the deflection at this point A, we are asked to calculate what is the rotation at this point B. So this point B is at the midpoint of the cantilever, so the total length of the cantilever is L. B is at a distance of L over 2 from the point C, and point A is L over 2 from point B. So in this case, you have a force that is being applied at point A, but we are asked to calculate what is the rotation at point B. So there is two things that you have to think about here. First of all, you are applying a force, but you are asked to find out the rotation. Secondly, we are not being asked to find out the rotation at the same point, but actually the rotation at a different point. So something like this could not be done using the equivalence between strain energy and the work done by the force P. Okay, so these are the cases where Castigliano's theorem is actually very, very powerful. Okay. Now, if you want to find the rotation at point B, the first thing we have to do is that we have to apply a dummy moment, because the moment and rotation are complementary variables. So if you want to find out the rotation, you essentially have to take the derivative of the strain energy U with respect to a moment, not a force. Okay, so that means that we have to assume a dummy moment at point B, because there is no actual moment acting at point B. Okay, so that is what I have done here. So essentially, I have assumed this dummy moment M prime to be acting at point B. Okay, here I have also done something that is a little bit counterintuitive. I have assumed that this bending moment or this dummy moment M prime is in the counterclockwise direction. Okay, but the reason that I have done this is because eventually when you find out the rotation at point B, it will tell you something that is very important. Okay, so that is the reason why I have assumed this bending moment or the dummy moment M prime to be in the counterclockwise direction. Okay, so what happens when you assume a bending moment M prime at point B? The first thing that you have to notice is that the internal moment function between the point C and point B and between the point B and point A are going to be different. Okay, if there was no moment at point B, then essentially you can describe the internal moment at any point between C and A with a single function. But now that you have this assumed dummy moment M prime, there is going to be a discontinuity in the moment function at point B. So essentially, you have to find out what is the moment function in AB and BC separately. So what I am going to do is, first we are going to look at the segment AB. So I am going to take a section somewhere between A and B, and the free body diagram looks like that. Okay, so essentially, this is the free body diagram. If you take a section between A and B and analyze the internal forces and moments. Okay, so there is going to be a force P that is acting, which is the external force, that has to be countered by an internal shear V1 of x. And there is also going to be a moment, an internal moment M1 of x. I have used the subscript 1 here because this is the moment in the segment AB. I am going to use M2 of x to denote the moment that is in the segment BC. Okay, so the M1 of x is the internal moment in segment AB. That is actually very trivial to calculate. So if you write the function, M1 of x is going to be nothing but minus P times x. Okay, and this is minus P times x because I have assumed the moment to be in the clockwise direction, but actually the moment will be in the counterclockwise direction. Okay, so that is the internal moment function between A and B. Okay. Now, if you look at segment BC, the internal moment is going to be somewhat different. Okay, and the reason is you have this moment M prime that is acting. Okay, I want to pause here for a minute and then explain something that is important. This m prime is a dummy moment. It actually doesn't exist. But for the purposes of applying Castigliano's theorem, you have to assume this dummy moment. Now, when you draw the free body diagram and then you find out what the moment function is, you have to include this dummy moment also in your analysis. You can't ignore it. Okay? So that is why you have this dummy moment m prime acting at point B. And then for the same way as you wrote the moment function for AB, you can also write the moment function for BC. Okay? And that moment function is going to be m2 of x, which is going to be m prime minus p times x. Okay? Because m prime is in the counterclockwise direction. So m2 will be opposite to that. So essentially m2 will be m prime minus p times x. Okay? So this is something that is very trivial. You all know how to do this. Okay. Now, once you have found the bending moments, essentially you can find out what the internal strain energy is. Okay. In this case, you are only having bending deformation. So essentially the bending moment square divided by 2EI times dx, integral from 0 to L, that is going to be your entire strain energy. Okay. Again, I want to emphasize this point. This here in this case, the strain energy is 0 to L m squared by 2EI dx because only a bending moment is present. Okay, if you have an axial force or if you have a torque, then you have to also take into account the torsional strain energy and the strain energy due to axial deformation to calculate U. Okay. Now, once you have this U function, your theta B is nothing but the derivative of U with respect to m prime. Okay, again, when you want to find the rotation at a point, you have to take the derivative of the strain energy with respect to the assumed moment there. So the assumed moment or the dummy moment in this case is m prime. So that is what you're supposed to do. So if you take this function U and then you take derivative with respect to m prime, essentially it becomes this. Okay, integral 0 to L of m over d or m over ei del m over del m prime times dx. Okay. Now we know that the moment function is not constant all the way from 0 to L. From 0 to L by 2 and from L by 2 to L, it has different functions. So essentially 0 to L over 2, that is the segment AB. So let me just point it out. This is segment AB and that is segment BC. So essentially the limits become 0 to L over 2 and L over 2 to L. So in this case, this is the moment function in AB and that is the moment function in BC. Okay, we have already derived these moment functions. So all that we have to do is essentially substitute those moment functions into this integral. And then we also have to find these terms, dm1 by dm prime and dm2 by dm prime. So those two things we still have to figure out, and that is what we are going to do next. Okay, so essentially we know m1 of x is minus p times x and m2 of x is m prime minus p times x. Okay, now here is a very important thing that you have to notice. We are taking the derivative of m1 and m2 with respect to m prime. We are not taking the derivative with respect to x. Okay, so you have to be very careful. If you think about this m1 here, it does not depend on m prime at all. So if you take the derivative of m1 with respect to m prime, the derivative is going to be equal to 0. On the other hand, m2 depends on m prime. Okay, but dm2 by dm prime is just going to be 1. This function here, px, does not have an m prime term. So essentially when you take the derivative of px with respect to m prime, it is going to be equal to 0. So dm1 by dm prime is 0 and dm2 by dm prime is equal to 1. So that essentially makes our integral much simpler. We don't have to worry about this term at all, this 0 to L over 2 term, because dm1 by dm prime is just 0. Okay, so we just have to worry about the second term, which is the integral from L over 2 to L of m2 times dm2 by dm prime. Okay, now m2 is m naught, this is actually m prime minus px over ei times 1 dx. Okay, this is del m2 by del m prime, and this is nothing but m2 divided by ei. Okay, now at this point though, we can substitute that your m prime equal to 0 because m prime is an assumed moment or a dummy moment or a fictitious moment. So it doesn't really exist. So now once we have taken the derivative of u with respect to m prime, we can substitute that m prime is equal to 0. Okay, so essentially the integral becomes even simpler. There's no m prime term at all. So you have just theta b equal to L over 2 to L of minus px dx over ei, and that turns out to be this quantity, minus 3pl square divided by 8ei. Okay, now here something interesting has happened, right? Because the theta b that we have found turns out to be negative. So what does a negative sign actually mean? What it means is that the rotation is in the opposite direction to the assumed direction of the moment. Okay, so if you look at m prime here, we assume that m prime is in the counterclockwise direction. Theta b being negative essentially tells you that the rotation at point B is not going to be counterclockwise, it is actually going to be clockwise. That makes a lot of sense. So essentially, if you have a cantilever like this, and then you apply a force P, what you'd expect is that for it to rotate like that. And this would be the theta, right? And that theta, by definition, is negative because it is a clockwise rotation. Okay? So all this symbol is telling you is that, this negative symbol is telling you is that the rotation is in the clockwise direction, which makes absolute sense given the direction of the force here. Okay? But the right way to kind of read it is that the rotation is in the opposite sense to the direction of the assumed moment. Now, if we had assumed this m prime to be in the clockwise direction, if you had taken m prime to be in the clockwise direction, what you would have found out is that the value of theta b is still going to be the same, but it will be plus 3pl square over 8ei. Okay, so that is the difference. So if you assume the moment to be in the clockwise direction, then you would have gotten a positive value. Okay. The other thing that I want you to notice here is that the final answer for theta b does not depend on m prime. Okay, even though we assumed this particular dummy moment m prime, the final answer doesn't depend on m prime, which also makes sense because it is not a real moment. The cantilever is just loaded by the force P. So the rotation at any point should only depend on P, not on anything that you assume. Okay? So this example kind of gives you a lot of different things to look at. So you have to make sure that you have to assume a moment because you're interested in rotation. You have to assume the moment to be acting at the point where you're interested in finding the rotation. And then you have to interpret the rotation in the right manner. Okay? So this is a very interesting example because it touches on a lot of things that are possible with Castigliano's theorem, but also points you towards some very important things that you need to take care of. Okay? Now let's look at a different example. So if you look at what we discussed maybe a few lectures back, we talked about how the energy methods can be, or the equivalence between the strain energy and the work done cannot be used to find out deflections or rotations where there are multiple forces acting. Okay? Or if you want to find out the reflection at a point where a force is not acting, that method is not going to work. So this example that we just looked at told you how you can actually find the rotation at a point that is different from where a force is acting. Okay? Now we are going to look at an example where there are multiple forces acting. Okay? And that will give you some more pointers on how to apply this Castigliano's theorem. Okay? So let's look at this example. Again, this is a fairly simple example of a cantilever. But in this cantilever though, there are two forces. So there is a 300-pound force here that is acting at the tip, and there is a 200-pound force here that is acting at this point B. Okay? And this length AB is 30 inches, and the length BC is 20 inches. Okay? In this case though, you are also given what the bending rigidity is in the numerical value. So it's 20 times 10 to the 6 pound inch square. So it should be, I made a mistake here, it should be pound inch square. Okay? And we are asked to find out what delta A is, okay, which is the deflection at point A. Now, in this case, you might be a little bit confused because you are asked to find out the deflection at point A, and there's actually a force acting at point A, and the force has a given value of 300 pounds. So how are you supposed to find out what the deflection is at point A? Because you have to take derivative of the strain energy with respect to the force acting at that point. So if there's already a force acting at that point, how are you going to deal with it? So in these cases, what you do is that even though there might be an actual force acting at this point, you still assume that that force is a variable force. So essentially what I'm going to say is that the force acting at point A is going to be PA, and the force acting at point B is PB. Okay. You can take PB to be a numerical value, but it makes sense to treat both these forces at A and B to be variable forces, because eventually, if you're interested in finding out the deflection at point B, then you can take the derivative of the strain energy with respect to PB and get delta B. So for this particular problem, I am going to assume that both the force at point A and the force at point B are variable forces, and they are PA and PB. Okay. Eventually, once you take the derivative, then you can substitute PA is 300 pounds and PB is 200 pounds to find the numerical value of delta A. Okay. So again, in this case, because there are two forces acting at point A and point B, the moment function is not going to be continuous over the entire length of the beam. So essentially, you have to look at the segment AB and segment BC separately. Okay. So if you draw the free body diagram for segment AB, this is how it's going to look like. And then you can find out what the moment function is. So again, here I have used M1 as the moment in the segment AB, okay, which is from 0 to 30 inches of x. So in this case, M1 of x is minus PA times x. And M2 of x is going to be a little bit more complicated because you have both the force PA and the force PB. Okay. So essentially, if you use moment equilibrium, say suppose you take moment about this point here, okay, at the cut, this shear force is not going to apply a moment. This PA is a counterclockwise moment. This PB is also going to apply a counterclockwise moment, and this M2, the internal moment, is also counterclockwise. So M2 is going to be minus PA times x minus PB times x minus 30. The reason that you have this x minus 30 is because the distance of PB from that point is x minus 30. X is the total distance, so this distance is going to be x minus 30. So that is why you have that x minus 30 in the moment equation. Okay. Now, again, we have found the moment function in both segment AB and segment BC. And again, in this problem, you have deformation only due to bending. So effectively, the strain energy is going to come only from bending deformation, and that is the strain energy due to bending. Integral 0 to L, M over EI. Oh, I actually made a mistake there. U is going to be integral from 0 to L, M squared over 2EI times dx. And if you take the derivative of U with respect to PA, that is going to be that integral. Okay. And again, the reason that we can do this here is because there's only bending deformation. Now, in this case, again, you are going to have to split the integral from 0 to L over 2 and L over 2 to L, because the moment functions are different from A to B and from B to C. Okay, and that is what we are going to do next. Okay, so essentially we are going to find del M1 by del PA and del M2 by del PA. Okay, again, I want to emphasize that you are taking the derivative with respect to PA, okay, not with respect to x. It turns out that for these functions, M1 is minus PA times x, and M2 is this particular function. Del M1 by del PA and del M2 by del PA both turn out to be minus x. So essentially, these two things are the same. Okay. So then all you have to do is essentially apply this particular equations that you have got for del M1 by del PA and del M2 by del PA, and then substitute into the integral. So again, if you look at this integral here, right, it is the first term is minus M1 of x, is M1 of x divided by EI, and the second term is del M1 of x by del PA. For second integral, the first term is M2 of x by EI, the second term is del M2 of x divided by del PA, or del M2 by del PA. Okay, and if you substitute these particular values of PA and PB, so effectively you know that PA is 300 pounds and PB is 200 pounds. So essentially you evaluate these two integrals, Okay, and then you substitute PA is 300 pounds and PB equal to 200 pounds, and that will help you get the numerical value for delta A. Okay, so that is how you find delta A. Now, I told you that we are assuming that the force PB is also a variable force, and the reason that we did that is because now if you want to find delta B, it's actually very simple. So what you have to do is you have to find, delta B is going to be del U over del PB, okay, and that is going to be the integral from 0 to L of M over EI del M over del PB dx, okay, and that is going to be nothing but the integral from 0 to L, okay, M1 integral from 0 to L over 2 M1 of x over EI times del M1 by del PB dx plus the integral from L over 2 to L M2 of x over EI del M2 over del PB times dx. Okay, we know M1, we know M2, so we can find del M1 by del PB, we can find del M2 by del PB. You can integrate all these integrals and you can find delta B. Okay, if we are assume that PB is a constant force, right, then you can't do this. Okay, so that is the reason why we assume PB to be a variable, so that you can also calculate delta B if you're interested. Okay, all you have to do is you have to integrate these two integrals and then put the value of PA and PB and EI, which is also given in this case. Okay, so this is an example where you had multiple forces acting on a structure, but you are still able to find out the deflection at a specific point using Castigliano's theorem. Okay. So in this case, if you are interested actually in finding the deflection, say at some other point here, say D, then what you have to do is that you will have to assume a fictitious force PD acting at that point D, and then write the moment function from A to D, D to B, and B to C, and then integrate over all three segments, and then find out what delta D is. Okay? So this method is actually very powerful. It doesn't matter whether you have a force acting at the point where you want to find the deflection, whether there is actually a moment acting at the point where you find the rotation, it doesn't matter at all. You can always assume a dummy moment or a dummy force to find out the deflection at a specific point. Okay? So in the upcoming lectures, we'll look at more complicated examples of how to use Castigliano's theorem to find out the deflections where the boundary conditions or the loading conditions are more complicated, or the structure itself is more complicated. Okay? With that, I'll end this lecture and I'll see you next time.